Okay, so good morning to all of you. Well, our today's class will be based on how to get any compound to be aromatic, non-aromatic, and anti-aromatic compounds. For any compound to be aromatic, non-aromatic, or anti-aromatic, it needs to fulfill a certain conditions. For example, for any compound to be aromatic, for any compound to be aromatic, it needs to fulfill a certain set of conditions. If it fulfills that conditions, that means the compound will be aromatic. Number one condition, it has to be cyclic in nature. Only cyclic compounds can be aromatic. Acyclic, all acyclic compounds are always non-aromatic compounds. Second rule which needs to be fulfilled is all the atoms in a cyclic ring should be planar. There has to be a planarity among all the atoms which are present in a cyclic ring. If an atom which is present outside the cyclic ring, it is planar or non-planar, doesn't matter. But the atoms which are present in the cyclic ring must be planar. And rule number 3 should be there should be resonance. There should be resonance throughout the ring. What is the meaning of throughout the ring? I will tell you with an example. And the fourth condition, which it needs to be fulfilled for an aromatic compound, it must follow the 4n plus 2 is equals to pi electron rule, also known as Hückel's rule, where n is should be equal to some integer value. If the value of n is non-integer, that means it doesn't follow that conditions. Okay. So these are the basic conditions for any compound to be aromatic. Well, if any of the first, second, or third condition fails, if any of the first, second, and third conditions fails, then the compound will be non-aromatic. For example, first I will write it down. If any of the first, second, and third condition fails, then it will be a non-aromatic. Non-aromatic. For example, if I will say the compound is not a cyclic compound. So if it is not a cyclic compound, that means it will be a non-aromatic compound. If all the atoms present inside the ring are not, any of them is not planar, that means again it will be a non-aromatic. If there is no resonance throughout the ring, that means it will be again a non-aromatic compound. Okay. And let us say if a compound, if compound follows first, second, and third conditions, but it fails in fourth condition only. Only then it will be a anti-aromatic compound. Let us say the first condition, that means it is cyclic, it is planar as well, it follows the resonance throughout the ring, but it unable to follow the 4n plus 2 is equals to pi electron rule. That means whenever we are placing that rule and n is coming out to be a non-integer value, that means in that condition, the compound will be anti-aromatic. Now, I will give you some examples of that, multiple examples of that, and by which you can easily able to understand, and just check whether a compound is aromatic, non-aromatic, and anti-aromatic compound. Suppose I will take the first example is like this one. This is called benzene ring. However, most of you know about that benzene is an aromatic compound, but we will have to check that how it follows all these conditions. Number one, it is a cyclic compound, which can be easily see that it is a cyclic compound. Number two, it is a planar. Look, in this benzene ring, all the carbon atoms, or 1, 2, 3, 4, 5, 6, all the carbon atoms are sp2 hybridized. And if they are sp2 hybridized, that means they are planar. If a carbon atom is either sp or sp2 hybridized, it will be always planar. Okay. So here we can see that all the carbon atoms contain a one pi bond, and hence it will be a sp2 hybridized carbon. So we can say that this is planar. And since there is an alternate double, single, double, single, double, single, that means there is a conjugation inside, the complete conjugation inside the ring. That means it follows that it has resonance throughout the ring also. Now the fourth conditions, let me see that 4n plus 2 is equals to pi electrons. So how many pi electrons are there? 1, 2, 3. There are 3 pi bonds. So the electrons would be 6 because every pi bond contains 2 electrons. So by solving that, we can see that this is n is equals to 1 here. And since n is equals to 1, that means it is an integer value. And since it is an integer value, we can say that this is an aromatic compound. Now, so if you want to check that it is aromatic, non-aromatic, or anti-aromatic, so what happens is we will have to follow, look, cyclic, we can easily see that a cyclic, whether it is a cyclic or a cyclic compound. But in every conditions, we will have to check. In every condition, every example, we will have to check whether it follows the second rule and the third rule. I will give you a very small trick. This is not any rule. This is just a trick so that you can easily able to get it, whether this compound contains the second, follows the second rule or the third rule as well or not. So the trick is, a very easy trick is that whenever you form any of the compound, okay, every atom which is present inside the ring, like there are 6 carbon atoms which are present in the ring. So I'm talking only inside the ring, not outside the ring. So every atom inside the ring must contains at least either a double bond, it must contain either a double bond or lone pair or any positive or negative charge. That every atom which are present inside the ring must contain at least one of them. Either it should contain a double bond, either it should contain any lone pair, or either it should contain positive charge or negative charge, any one of them. Example, I will tell you. Look, for example, we have this compound and I'll put a positive charge here. I want to just check. This is a cyclic compound. We all can see that. I just want to check that whether it follows the second rule and third rule or not. So for that, we should not make any resonating structures and check. We can directly check and answer the question. So what I've told you, the trick is that every carbon atom should contains either a double bond or a lone pair or a positive negative charge. We can easily see that this carbon, let me just number them. 1, 2, 3, 4, 5, 6. I've randomly numbered them. So first carbon atom contains a double bond, second carbon atom contains a double bond, third carbon atom contains a double bond, fourth contains a double bond, but fifth does not have a double bond or a lone pair or a positive charge or a negative charge. That means it fails for second and third conditions. And if it fails on the second and third conditions, that it does not contain a resonance throughout the ring. All the atoms are not one planar. Like fifth carbon atom, there are one, it is sp3 hybridized, and hence it is a non-planar. So we will say that this compound would be non-aromatic compound. Got it? So for second and third conditions, we will easily go through with this trick. Either it should contain a double bond, lone pair, or any positive or negative charge. I will give you one more example for that. Let us say we will have to check about this. So can we easily see that it is a cyclic compound? Can we easily see that every carbon atoms contains at least double bond or a lone pair or a positive charge or a negative charge, one of them. So one, two, I see randomly, I'm just numbering them randomly, not according to the IUPAC naming. 3, 4, 5. So we can easily see that the one carbon atom contains a double bond, 2 contains a double bond, 3 contains a double bond, 4 contains a positive charge, and fifth contains again a double bond. So I can say that it follows the second and third conditions. Now moving on to the fourth conditions, that is 4n plus 2 is equals to pi electrons. Here we have two double bonds, that means 4 electrons. And as you know that positive charge does not contain any of the lone pair. So 4n plus 2 is equals to 4 only. So here we can see that value of n is half. That means it is not an integer value. So that we can say that it is a anti-aromatic compound. It is a anti-aromatic compound. Now, I will give you one more example. If I'll put a negative charge here, now okay, we can easily see that it follows first cyclic resonance throughout the ring, because the trick follows that every carbon atom contains a double bond, negative charge or a positive charge. Now moving on to the fourth conditions, which is 4n plus 2 is equals to pi electron. Here we can see that there are two double bonds, that is 4 electrons, and negative charge also contains 2 electrons. So the net number of electrons is equals to 6. So we can say that n is equals to 1, which is an integer, hence it will be a aromatic compound. Okay, let me give you one more example. Let's talk about this one. It is a cyclic compound. Every carbon, let me go to the direct part. It follows the second and third conditions, because every carbon atoms contains a double bond or a negative charge, right? So let us follow the fourth condition, that is 4n plus 2 is equals to how many electrons? We can see that 2 electrons from the double bond, 2 from this negative charge, 2 from this negative charge, and the net would be 6. So here we can see that the value of n is equals to 1, and it is an aromatic compound. Okay. Again, if I'll put a positive charge here. So again, it is a cyclic. It follows the second and third conditions. 4n plus 2 would be equal to only 2, because positive charge does not contain any electron. So from this side, n is equals to 0, and 0 is also an integer value. That means this is also an aromatic compound. One more example. This is a three-membered cyclic ring. It follows the first cyclic compound, follows the second and third condition as well. Again, 4n plus 2 is equals to 2, n is equals to 0. That means it is a aromatic compound. Similarly, if I'll put a negative charge here, it follows first, second, and third conditions. Similarly, 4n plus 2 is equals to how many electrons? 2 from this double bond and 2 from this negative charge, that is 4. N is equals to half, which is not an integer value, which means it fails for the fourth conditions, and this compound would be anti-aromatic. Okay, again, if we will talk about this one. So it is a cyclic. Yes, resonance throughout the ring, planar as well. So 4n plus 2 is equals to 8 this time, because there are two pi bonds and two negative charge that contains 4 electrons. From the negative charge, 4 electron from the pi bonds. So that means net n is equals to 4n is equals to 6, then n is equals to 3 by 2. That is not an integer. So if it is not an integer, that means it is an anti-aromatic compound. Got it? So by this way, we can easily check whether a compound is aromatic, non-aromatic, and anti-aromatic. I will go with another compound, this one, which is called pyrrole. Make sure you have to learn the name of this compound as well. This is called pyrrole. And in this case, nitrogen contains a lone pair as well. So in this case, the nitrogen atom does not contain any positive or negative charge or a double bond, but it contains a lone pair. As I told you earlier, that every atom present inside the ring must contain at least one species, and that one is a lone pair, negative charge, positive charge, and a double bond. Nitrogen contains a lone pair. So 4n plus 2 is equals to 6. Why it is 6? Because 2 electrons from this pi bond, 2 electron from this pi bond, and the 2 electrons which are present on the nitrogen atom, which is obviously in resonance with the double bonds. So n is equals to 1, and hence pyrrole will be aromatic. Similar example is like furon. Okay. Similar example is like a furon. Let me just draw it properly. Sorry. Okay, in furan, oxygen contains two lone pairs. This is called furan. In furan, oxygen contains two lone pairs. But if any atom contains one lone pair, two lone pair, or three lone pair, make sure only one lone pair can undergo in resonance. The other one cannot. So oxygen atom contains two lone pair, but only one lone pair will be present in resonance. So if we are going to count 4n plus 2 is equals to pi electron, we will only count one lone pair, that is 2 electrons from this oxygen, 2 electrons from this double bond, 2 electrons from this double bond. That will be only considering 6. N is equals to 1. That means it is an aromatic compound. Okay. Now, suppose I will give you one example where there are two rings attached with each other, and this one is the case. Okay, so since there are there are two rings, one ring is this and the other ring is this, you can easily see that this particular ring, the left ring, contains double bond on every carbon atom. It is like a benzene ring, right? So for this ring, we can say that 4n plus 2 is equals to 6, n is equals to 1. That means this ring, this benzene ring, is again an aromatic. But if we'll check about this ring, this atom does not, this carbon atom does not contain any double bond, positive charge, negative charge, or a lone pair. Hence, we can say that this ring should be non-aromatic. But if any compound, contains one aromatic ring and the other one is a non-aromatic, we will say that this overall compound would be an aromatic. Because if one of the ring is aromatic, then we will say it aromatic compound. Okay. Yep. Suppose we have another example of a 7-membered ring. This is called tropolone. This compound is called tropolone. Now, what we can see here is this oxygen atom is present outside the ring. So we will not count, we will not check whether it contains a lone pair, whether it contains a double bond. However, it contains a double bond, but we will not going to check on that. We will only going to check about these which are present inside the ring like this. So there are 6 carbon atoms inside the ring, and this double bond is majoritarily shifted on the oxygen atom. Because oxygen is more electronegative, it will contain this negative charge, and this carbon atom contains a slight positive charge on it, right? This contains a delta negative and this contains a delta positive. So we will not count, this carbon does contain a double bond on it, but we will not count this double bond in the 4n plus 2 rule, because this double bond is present outside the ring, and in major conditions, these double bond lone pairs are majorly shifted on the oxygen atom, not on the carbon atom. So I can say that 4n plus 2 would be equal to 6 only because of these 3 pi bonds. So n is equals to 1, and hence it will be a aromatic compound. So I can say that propolone is an aromatic compound. Okay, guys, let's moving on to the next part. Suppose we have this aniline part. This is called aniline. So the lone pair present on nitrogen atom, but they are present outside the ring. We will only have to check inside the ring part. So we will only talk about this ring. And we all know that we have checked this, that this ring is aromatic. So outside the ring, whatever is there, we will not count them. We will only talk about the ring. We will only calculate 4 and plus 2 inside the ring. We will only calculate the 1, 2, 3, 4 conditions inside the ring, not outside the ring. So this compound would be again an aromatic compound. Suppose we have two cyclic rings which are attached to each other via a single bond. There are two different cyclic rings, one on the left, one on the right, and they are attached through a double bond. Talking about this compound, these are the two cyclic ring, but they are fused with each other. Fused, I can say that the two carbon atoms are common between the two rings. But here, no carbon atom is common. Here, the two rings are attached with each other through a single bond. So we will have to check separately. So this ring on the left is aromatic. This ring on the right is also aromatic. We all know that 4 and plus 2 is equals to 6. We have just checked multiple times about the benzene ring. So we will answer them separately. The left ring is aromatic. The right ring is also aromatic. We will have to answer them separately when the two cyclic rings are attached through each other via a single bond. Okay. So if we will check about this compound, whether this is aromatic, non-aromatic, and anti-aromatic. So we can easily, just by seeing that, we can say that this one carbon atom does not contain any double bond, positive charge, or lone pair. That means it is a non-aromatic compound. It is a non-aromatic compound. So by this way, we can easily check whether a compound is aromatic, non-aromatic, and anti-aromatic compounds. Guys, overall, if we will check about the stability of these compounds, so in overall, aromatic rings are the most stable compounds. Aromatic compounds are the most stable among them. After that, there will be non-aromatic compounds and anti-aromatic compounds. Anti-aromatic compounds are highly unstable. As I can say that aromatic compounds are highly stable, the similar manner I can say anti-aromatic compounds are highly unstable. And about this, these are the compounds which are highly stable compounds. I will give you one example for that. Suppose I have this cyclic ring with a positive charge on it, and I have this cyclic ring with a positive charge on it. Clearly, as we know that the carbocation stability depends on the resonance. Greater is the resonance, the carbocation stability is more. We have discussed that part in the last class. But here, we have a carbocation and there is one double bond. We have a carbocation and there is two double bonds. I can see that the left side compound, the compound number 1, and this is the compound number 2. The compound number 1 contains lesser resonance as compared to the compound number 2. Because in this case, the positive charge can undergo in resonance with only one double bond, while in this case, the positive charge can undergo in resonance via two double bonds. Yet, the first compound is more stable. If we will talk about the stability, the first compound is more stable than the second one, because if I will check the aromatic, non-aromatic, and anti-aromatic part among these two compounds, I can say that the first compound is cyclic, there are resonance throughout the ring, and it is a planar also, and it follows 4n plus 2 is equals to pi electron, which is 2, n is equals to 0, hence it is aromatic, which in this case 4n plus 2 is equals to 4, and n is not equal to an integer value. That means this compound is anti-aromatic. So as we know that anti-aromatic compounds are highly unstable compared to the aromatic, that is the reason the first compound is highly stable one as compared to the second compound. Got it? So whenever we have any positive charge or a negative charge, if that compound becomes aromatic, then it will be more stable. While if the compound becomes anti-aromatic, it will be unstable. It will be unstable because aromatic, non-aromatic, and anti-aromatic aromatic compounds are the most stable one. So in the next class, we are definitely going to see in detail part how these aromatic compounds becomes more stable and how these anti-aromatic compounds become highly unstable. Okay. Thank you so much for this. Let me wind up this class.